Right, I guess that we can start. Hello, everybody. I don't know if you can hear me. So I'll be heading the panel session, the last session for our workshop. And it will revolve around two main topics, this being federated learning and collaboration or offloading of computation from mobile agents to ambient local devices. Our participants in this session are Dr. Amanda Prorok, who is an assistant professor in the Department of Computer Science and Technology in the University of Cambridge and a fellow of Pembroke College. Her lab's research focuses on multi-agent systems and multi-robot systems, and their mission is to find new ways of coordinating artificially intelligent agents to achieve most common goals. She has been honored by numerous research awards, including ERC Starting Award, an Amazon Research Award, the EPSRC New Investigator Award, the Isaac Newton Trust Early Career Award, and several Best Paper Awards. Next, we have Dr. Dimitris Papailiopoulos, who is an assistant professor of electrical and computer engineering at the University of Wisconsin, Madison, a faculty fellow of the Granger Institute, and then a faculty affiliate with the optimization group at Wisconsin Institute for Discovery. His research lies in the intersection of machine learning, coding theory, and distributed systems. Dimitris is a recipient of various awards, such as the NSF Career Award in 2019, two Sony Faculty Innovation Awards, the Benjamin Smith Reynolds Awards for excellence in teaching, and many other Best Papers awards. Last but certainly not least, he is also one of the co-founders of the MLC's conference. The rest of the panel you already know, but just for completeness sake, for those who just joined the workshop, we have Dr. Fahim Kawsar, who is the founding director of Pervasive Systems Research at Nokia Bell Labs, Cambridge, and holds a Design United professorship at TU Delft in the Netherlands. His focus is on building sensory AI systems that explain human behavior. And we have also Dr. Ilias Leontiadis, who is a colleague, and he's currently a senior research scientist at Samsung AI in Cambridge. His research revolves around mobile systems, deep learning, and networks. He's currently working towards supporting AI on mobile devices through distributed computing. His research nowadays revolves around DNN workload offloading to remote resources and federated learning. Welcome, everybody. I hope everybody can hear me. Everybody is actually muted, so I'm not really sure that you do.
Yeah, we can hear you.
Great. I don't see, for some reason, Fahim.
You see me now?
Yes, I do. Great. So let's start with the very popular topic of federated learning. Federated learning is coming to be the new status quo for training deployed NNNs in the wild by bringing model training closer to the source of data, that is the user's device, without sacrificing on the privacy side. Apart from leveraging the compute available in the wild in the form of today's smartphones or sensor networks, it also models data as being non-independent and identically distributed, which is largely the case out there. However, it also brings significant challenges in fairness, distributed optimization, and embedded compute efficiency. Simultaneously, federated learning finds traction in cases of few entities that do not or cannot exchange data due to legislation and privacy, for example, hospitals or insurance companies, and all share the benefit of training a common model without access to each other's data. Let me start with Dimitris and Ilias, and I would like to ask you, what do you see as the forefront of current research in federated learning? What are the biggest challenges that prevent the industry from adopting federated learning as a mainstream training scheme? Apart from the big players, of course. Dimitris, do you want to start, maybe?
Yeah, sure. Yeah. Well, I don't know if I'm the right person to answer this question, but yeah, I think there's maybe the biggest question for federated learning. There's of course, there's Google that things clearly work well for them. They've adopted federated learning for text prediction and a bunch of other things. Most of them arguably not mission critical. I think the success of federated learning for Google vastly lies on the fact that they have a very large user base, which implies that you have a lot of data that kind of like, will lead to improvements in accuracy for personalization when you do, multiple rounds of kind of like federated learning to aggregate and fuse the models. But I think, one big question is like, to what extent these benefits still hold for other, maybe smaller scale companies that are still interested in training distributed models while maintaining privacy, compared to, let's say, just doing the simplest of things where, I have a globally, the model will never start from like a random initialization. There will be some good, global model that will be fine-tuned at the user side. And I guess my question is, if you just do one iteration of federated learning, well, you just like zip the models just once, and then you fine-tune locally in, let's say, a smaller scale setting, not Google, some other, company or maybe a startup. Is there any benefit in doing multiple rounds of federated learning? So I think that's kind of like a question that, of course you can prove things about it, but I haven't personally, I'm not convinced that kind of federated learning is sort of the answer to all the privacy-preserving decentralized learning that you can get. So that's a big question. So the other question for me that actually has to do more with regards to the robustness of these systems, right? So we've had a recent paper that's going to appear at NeurIPS that essentially tries to understand to what extent someone can backdoor federated models in the sense of kind of like inserting sort of a malicious backdoor that can make the model, force the model do weird stuff for subtasks of the classification. And what we see is that essentially federated learning, and that's also true for basically any other machine learning model or training algorithm, is actually very amenable to what we call backdoor attacks on very rare edge case data. So edge case data are basically things that are very normal part of the input distribution, but are not likely to be part of the training or the test set. But once in a while there will be, and the backdoor kind of forces those models to do weird stuff. And that weird, the weird things that they can do actually can lead to very offensive labelings or very offensive predictions that you don't normally have in a well-trained model. And we basically saw that these types of kind of like edge case vulnerabilities, or like, vulnerability, like, the performance on rare data is sort of hard-coded in high complexity models. And it's not just a problem of federated learning, but why it becomes a problem of federated learning is the fact that, you have user data that you can't really, validate the sources. You can't really kind of like look into the data because Google, for example, has vowed to not like look into the actual data set or the models of the users. And this creates a bit of a problem. So I can see that this could be a challenge for, companies where, federated learning will be applied to something beyond text prediction. That's kind of like, maybe not that mission critical, to things like healthcare or something even more mission critical than that, right? In these cases, very similar to how you're doing like a bank transaction and you're given with like an encryption guarantee that this thing will not break unless you factor integers. This type of security and robustness guarantee we don't really have right now for federated learning, at least in the general case. So I think these two aspects, the aspect of robustness and the aspect of, how much do I get from having users participate in multiple rounds versus just like a single round where they fine tune, and whether there's a gain in accuracy with regards to that. I think these two challenges are still, it seems to me they're still open and are very interesting.
I see what you're saying. And essentially it's the tail of the distribution that the malicious actors are aiming for, and robustness fails around there. But on the other hand, you talk about maybe having a smaller scale, but this smaller scale, maybe you're able to validate better at least the edge cases that this system fails with.
Yeah, that's a very good point. If you cannot have the ability to validate users, say for example, I'm Google, and in my federated learning, only my engineers' data will be used for training. And then you're like, okay, nobody will adversarialize, exactly because of what you said. This is a very good point. So you could have something like this. You could have kind of like a verification of the users that are actually participating, and the robustness of the system kind of like relies on your trust on them to kind of do the right thing. But yeah, that's a great point.
Ilya, coming to you from the standpoint of the big players, what's your take on the big challenges from your standpoint?
Right. So the biggest challenge is the challenge I think is hindering the widespread deployment of federated learning is the lack of actual applications that have labeled data that can be harvested in large scale by all of these devices. So if you talk about Google and Apple, practically the best kind of case scenario for federated learning is next word prediction. And of course, you always have the label for these kind of scenarios, which is the next word that you're trying to predict. However, if you go to other types of models that are used in real life, like context awareness, speech, face recognition, landmark detection, and so even for anomaly detection that I was talking about, you don't have the label, and users are very reluctant to manually label data sets in large scale to help a company to achieve a better goal. So that's one thing. How can you actually train a federated learning system that kind of works with in a kind of unsupervised way, if you like? The other thing is, I think the biggest, another hindering factor is that the libraries that are out there to practically deploy federated learning and on-device training are a mess. Essentially, they don't exist. If you try to practically do on-device training, you have only 1 or 2 options, and they barely work. If you want to do this in a privacy-preserving way, again, all the libraries you have to include for differential privacy and secure aggregation are a mess to put together into a package that works. So, and the third thing is that you actually, and that's why mostly device manufacturers actually can do that, is that you need some support from the OS as well. You need to make sure that your application will not be killed. You need some low-level permissions. You need some kind of let's say, engineering on more kind of the root low-level support of the device, which is almost impossible for small developers. If you're like maybe Facebook or whatever, you can design your app in a very smart way that kind of bypasses some of these limitations, or even go to Google and Apple and say, hey, you should implement this because I need this to support 7 billion people. But if you're a smaller player, it's impossible to do this. And the other thing, I agree about robustness. It's impossible to predict the outcome of the model, especially guarantee privacy, guarantee membership attacks, guarantee all of these things. And finally, the more controversial way to attack this is that, in a way, a lot of people still don't care that much about privacy as much as they should. So they are comfortable clicking, okay, give data to this third-party provider to store in the cloud and train the model in a global way. So privacy is not the main focus of users to enforce privacy protecting, privacy, let's say, ways to train models in a more privacy-preserving way. The public is not yet that mature to demand this from companies, and they're let's say cloud training is still a thing because as a result of that.
I see your point, Ilya. I have only to disagree maybe to the OS part being an integral part, because essentially failure is integral to federated learning at large scale. So you don't expect robustness out of every client out there. But all the rest, the issues that you have heard, especially the labeling problem, is spot on to the deployment of large scale solutions. So going to Amanda and Fahim, how relevant do you see federated learning deployments in the embedded use cases, such as robotics or wearables or sensor specific hardware? What are the main challenges that federated learning is going to solve there? And what are the main challenges that it's going to bring, actually, doing federated learning on embedded hardware? Amanda, if you would like to start.
Sure. I can say a few things to that. So what's really interesting is, so I'm speaking from somebody who's from the robotics world, multi-robot systems, multi-agent systems. And surprisingly, or perhaps not so surprising, federated learning is not really a big topic yet in our domain. So there are a couple of people who are starting to tackle this problem, but it's very, very in its infancy. And I think that, well, there are a couple of reasons for why this is. So first of all, the multi-agent learning is going through a lot of kind of small revolutions these days, a lot of new innovations coming in there. But what hasn't changed a lot is the training execution paradigm, which is centralized training, decentralized execution. And there are a lot of reasons for this. The first reason is that most people assume homogeneous multi-agent systems because heterogeneity is something that is really hard to deal with, really hard to model, be it from a first principles-based approach or from a machine learning-based approach. And as you all mentioned before, we have this assumption of identically distributed data that we need to rely on for federated learning to work, right? And okay, sure, if we're assuming homogeneous multi-agent systems, perhaps one of the base assumptions would be satisfied. But the problem is, as soon as you start deploying this on actual physical platforms and they're acting in their own world and every piece of hardware is a little bit different and physicality matters, everything just breaks, because we're not talking about apps within a kind of sandbox ecosystem that is an iPhone or an Android telephone. We're talking about robots that are maybe composed of off-the-shelf components or autonomous vehicles that are all a bit different because of wear and tear. And I just feel that this whole idea of federated learning becomes infinitely more complicated as soon as you talk about embodied agents that actually interact very intensively with the physical world. So maybe that's one of the reasons that I think federated learning is still in its infancy. I think one of the other issues is data efficiency. So sim to real is one of the biggest problems in deploying learning solutions to robotic systems, where the challenge really is, well, we rely on simulation a lot in robotics because we train our systems. So control is difficult, right? And we train our systems for millions of hours in simulated time before we can get policies that do something that's reasonably acceptable and reliable, right? And how do we even think about that in terms of federated learning, where we're actually talking about actual systems? Because that's what we want to use it for, right? There's no point in spinning up multiple simulations that would just not do the idea of federated learning much justice. So I think that is one of the other issues here, that it combines the aspect of physicality and real-world tuning of our parameters with this whole aspect of combining it to models that are meaningful on actual physical platforms. But maybe this is a good point where we could hand it off to Fahim to take up.
Well, Amanda, I think you covered pretty much everything I wanted to say, so maybe I just say whatever she said is correct. No, but it's true. I think I was trying to hint that in my talk also, that the heterogeneity issues that you observe in real-world sensory systems, be it the wearables or robots or any kind of artifacts that has a physical manifestation, is very different than next keyword prediction, right? Because it's a very dynamic systems and the data qualities varies a lot, even for the same type of devices. If it has a different age, it will behave differently, simply because of the duration of the hardware. So it's incredibly hard to actually assume this uniform distribution that typically we take for granted, because in real world it's not uniform. You would have huge variety and huge heterogeneity in your different devices in different distributions, and it makes it extremely difficult to have a generalized framework addressing this learning, collaborative or federated learning, however you define it. And the second aspect is the trigger. I think Valentin was asking me that question, which was very relevant, that when to trigger and how much to tune or sort of like adapt. It's unknown to us today, right? I mean, we don't really know, for example, at what point your device needs further training or, like a further improvement, and how long that refinement will maintain its value. It could be for a very short time because of the mobility situation the user is in, or because of the contextual environment the user or the device is in. And it might go back to whatever model or whatever type you had before because the situation has changed. I think such external triggers are very critical in identifying the moments where this thing has to happen. And I don't think, at least
Fahim, I've lost
more
him
thoughtfully
for a while.
that when and how frequently and more importantly when to revert back of your models.
Fahim, if you'd like to repeat the last sentence, because I think there was a connection issue there. Just the last sentence that you said. About
all right. So I was just trying to emphasize that it is very important to look into these questions in a more systematic way to understand and identify and devise techniques that will allow us to determine when to start, for example, fine-tuning or learning in this kind of different devices, and when to revert back to your, whatever model you had in the past. That might work very well simply because the situation has changed and so on.
Definitely.
And the last piece I want to really talk about is, it's still an academic ball game, right? The federated learning, collaborative learning, we are still very much writing mode, to be honest. The thing is that when you actually start going to deploy these systems in real world across different industries, there will be a massive challenge with respect to data ownership. Okay, and we have to start thinking about that, right? So today, maybe the couple of big companies which basically manages our devices, sensory devices, are taking care of this. But if industrial IoT, well, it seems like it will emerge given the saturity in the industry right now. I think it will be a mess with respect to this kind of techniques, because the data will be crossing boundaries and borders of industries and different corporates and different, and then the question comes, the ownership a lot. I mean, yes, we are doing the privacy preserving locally, training and so on, but you will still need to share a little bit of your, gradients and so on to make sure your model behaviors are what you expect. And I think that would be an interesting question, how you address those data challenges, ownership challenges.
I think it's definitely going to be tough to explain to the legislators what the gradients are and what the role is actually in data privacy. However, you touched upon a lot of issues actually. One big difference between the status quo right now and the embedded case is energy budget. Right now, in the mobile setting, you tend to train this in a federated manner. You tend to train locally when you're plugged in and connected to Wi-Fi. However, when you have a robot with actuators going out in the wild, not in a controlled environment, as Amanda mentioned, or a sensor or IoT, sensor networks that are not connected to power but are battery powered, you need to be much more frugal and much more smart about your how you're managing the energy budget that you have. Would you like to comment on that, both from the one point and the other point?
Yes, absolutely. I think, I mean, I still feel, sometimes you manufacture the problems in a way that makes our research relevant. So in real world, I think in many cases, we will be not running many models or many trainings. To be honest, if you think about, again, I'm really talking about industrial scale physical artifacts, maybe robots and so on. These things are very mission critical, right? So you can't really tolerate even 5% or even 2% error rate in many cases, simply because of the mission criticality of the systems. So efficiency or energy efficiency will definitely, it will always be a challenge. I mean, given the small devices and the memory and the compute budgets we have. But I still think, like the question I was referring before, that if we have a systematic way of identifying when and how much to train, then I think identifying the right moments may be a bit plausible. So I was hinting towards this kind of energy autonomous systems. So typically when you see, I mean, if you think about really crazy outdoor applications, if you have and it's running on harvesters and so on, you would sometimes have surplus energies, right? And you might leverage those moments to perform these housekeeping stuff, right? The question is that whether that would be relevant for the performance that you are expecting to maintain the utility of your entire sensor network or not. I don't think at this stage we have a very good understanding of the subject matter. So what I'm saying is purely based on speculation, right? But the fact is that I would say there needs to be a systematic research in identifying those opportunistic moments where you have surplus energy that you can repurpose for housekeeping, or sort of like retraining your models, or fine-tuning your models, or reshaping your your gradients.
Yes, I agree. Amanda, is this the case also for robotic use cases, or even other agents such as self-driving cars?
I think, it's interesting. I don't think that a lot of people in the robotics domain are giving too much thought to the compute that machine learning takes, not extremely seriously. I mean, I don't want to lean too far out the window here, but my intuition is that this isn't a major issue yet, because we have really big problems that we're still not able to deal with. Like drones have a flight time of 10 minutes. No matter how big your drone is, the weight of the payload of the drone increases as the battery increases. And so we're just at this kind of 10-minute drop off, no matter what we do, right? And that's just fundamental. So payload is just an issue. When we talk about autonomous vehicles, we're trying to reduce our dependency on active sensors like laser rangefinders and those that really cost a lot of energy to run. Like that's what's really a headache for many people, or other autonomous agents that actually have to carry payload. And I think this is currently what keeps a lot of researchers in robotics up at night. I think, yes, so compute, learning, training will definitely come to be a problem in the near future. I think maybe more than the energy efficiency issue is more memory. So compressing models, I think that's what people are kind of looking into, perhaps before they would look into the energy efficiency issues. If you move into the area of sensor networks where you're not actually dealing with autonomous agents that are mobile, it changes slightly. So the IoT area, maybe the discussion there looks slightly different, because you actually don't care so much about payload and having to carry around your weight. But yeah, again, I don't want to lean out too far the window and make conjectures about what other domains are thinking about this issue.
Yes, I understand that essentially compute right now is lower in the priority list of robotics, at least because there are more important tasks to solve. So there was this issue of heterogeneity playing a central role in federated learning. Dimitri, from an optimization point of view, what do you think is a good design, or not a solution, but like the trajectory that we're heading towards with gathering gradients amongst heterogeneous targets? And if you want to correlate that with the fairness part of federated learning, which is a big issue. Actually.
Yeah, that's a very good question. I mean, it's very open-ended because there's heterogeneity in like so many aspects, right? So there's of course, whatever federated learning runs over Android, and Android runs on a bunch of different hardware. So there's that part, like the hardware heterogeneity. There's heterogeneity in things that I wasn't even thinking about. Some users, it's like night and day during different times around the world, right? So you have this type of some users can participate only during that time window. Other users can only participate during that time window. And of course, there's data heterogeneity, that it's not just kind of like the imbalance of data, that some just have more of a particular class, but even the context of the data. For example, for text prediction, you have people that come from all sorts of different backgrounds, that they use different styles for language. For example, you have whatever in the US, you have all sorts of different ethnic background, Americans and non-Americans. You have, immigrants like us that, we just like write in a different way. We sometimes write in whatever Greek lists instead of English and whatnot, right? So I think that's a very big issue, and it's unclear to what extent this can be mitigated. I think, there's been very interesting work in trying to somehow, bridge the gap between, or sort of like uniformize things a little bit, so that like the accuracy of different users does not suffer compared to other users, because precisely kind of like the goal of federated learning is that, you stand to benefit by participating in this thing, and not only your data is useful, but whatever the model learns from other users' data. But at the same time, you kind of want to make sure that, like, if your model was only just trained on your data, it wouldn't be more accurate, right? So, and that's where really a lot of fairness issues come up, and there has been a lot of interesting work, especially by Ginger Smith from CMU, where she's been looking into this sort of fair kind of like allocation problems of looking at different metrics that we have to optimize, such as kind of like looking at the maximum, the minimum, kind of like maximum minimum accuracy across all users, just to uniformize things. Because if you sort of look at the metric of kind of like what's the average accuracy that everybody gets, that's definitely not representative of everybody's experience, right? So I think from the perspective of optimization, there's a lot of interesting things you can do. You can always, change the distributions that you sample data points, and this is kind of like one of the proto algorithms that the federated learning team has suggested in the beginning, where you essentially, you sample and you reweight your gradients according to how many data points you have at hand. Of course, there's also, changing your loss that so that you accommodate for sort of individual users more than you do for the kind of like the aggregate measure. And there's other interesting questions, like we definitely know that from an optimization perspective, there's nothing as good as a uniform sample from your data, right? But the fact that these models are locally trained on very sort of biased, let's say, versions of the model when you do fine-tuning, that kind of like breaks this whole idea of uniformity. So we were thinking kind of a couple of years ago about, what if you could shuffle some data around, right? So what if, I have a trusted group of friends, and then privately, we do a data shuffling, and then I get some data points from whatever, my wife's, my mother's, my cousin's phone or whatever, so that like there is some breach of privacy, but not as crazy as like, someone else looking at my photos like a different part of the world or whatever. And this could improve things, right? But that complicates.
One might argue that you'll get the consent of sharing your or anybody's data with somebody they know much harder than somebody that they don't know. So there is also
that's actually that's a very good point. That is a very good point. Anyway, but I guess maybe the point I'm trying to make is that, there are some interesting ideas of how you can do, of course, private data shuffling, but also how you can learn on like, on data that's encrypted, so that you can like, shuffle around encrypted data through like, there's been some interesting work on like homomorphic encryption combined with training. Anyhow, but I think, there's like way too many challenges of non-homogeneity, and I'm not quite sure, what's the right one to tackle, because, from the theoretical perspective, there's only so many things you can model, but it's unclear to me. I'm not close to the, to the practice, like to whatever people are doing at Google. They share with us some of the things that they're doing, but they're not really telling us, how the users are selected, what parts of the data set is selected, how many HDD iterations are you running on its device, right? I'm sure they're doing the right thing, but I think when we have sort of like this distance from what's happening in practice, which is, I think, one of the biggest problems of federated learning research, it's hard to tell which non-homogeneity part is an issue. Is it the hardware? Is it the timing? Is it the weight? The imbalance of the data and whatnot? But there's definitely, it's fair to say that there's way too many non-homogeneity issues going on.
That's true. Ilya, from your standpoint, are we ready for on-device training at all, or we're not there yet? Both from hardware and framework side, I guess.
Yeah. Before that, I want to add something to the previous points discussed. Practically, I want to mention that heterogeneity is a big issue. I touched upon also in my talk as well, and there are multiple solutions that people have designed. I want to touch upon the fact that the main problem for me is that we don't have a way of actually measuring this in when we train our federated learning and simulate our federated learning algorithms out there. So if you think about this, the data sets we have is ImageNet that we somehow shuffled around to have different emulated devices that have different labels. We have Leaf, which has a bunch of data sets coming of different users, but none of them are essentially real-world heterogeneous scenarios where you have things coming from different countries, different popularities. So how can we actually measure convergence, and how can we measure privacy leak, and how can we measure the problem that this skewness is posing in our simulations if we don't have real-world data to actually measure this? And if you think about the solutions about training in heterogeneity, things like dropping stragglers, or training with fewer data to devices that are less capable, or asynchronous federated learning to allow for these kind of situations. We don't even know the kind of distribution that these devices are out there are contributing to our model. There are no such analytics about how many of these devices actually take place in a round of federated learning in the real world. So it's very challenging to actually analytically predict what will be the outcome without such data sets. So I think the community should spend a lot of time first to curate this kind of real-world data sets that can help us address these challenges before even going into solutions. And sorry, your question.
Yes. So my question was about. So it's very tightly related to that. So my question was that: are we ready for on-device training at all? Like, do we have the capability, the compute memory, energy capabilities right now, or the framework support to deploy it out in the wild? And if we have that, is it siloed under closed source of the big players, or can academia actually participate in the round of federated learning, let's say, and contribute actively to the area?
So the situation is getting better. I would say if you asked me 2 years ago, I would say that there's no way that someone from academia will actually be able to access on-device training and run things. Recently, there have been more and more support from libraries allowing some sort of on-device training, but this is more in terms of personalizing a few last layers that you can actually do on device rather than training a whole network or affecting the whole network. It's still, I would say, in its infancy. I think currently there is no standard way of both academia and actually small developers to deploy something that is trainable and adaptable on the real world. And clearly, this infrastructure is available in bigger players like Google and so on, and they have not yet released this to the public. Although I have seen quite a lot of promises that this will be something that will be released in the future. So I think it's getting better. I'm kind of optimistic about the fact that we will be able to do on-device training, but this training will never be on a full-scale large model. The memory implications of doing that and the data that are required to do this are impossible. But maybe fine-tuning and personalization and federated learning is something that will be something that we will be able to do in the academic world in the next couple of years.
I want to add a couple of things here. I think I'm not sure about our participants, but I think the skill sets, it's quite interesting. I observed this in my hiring decision as well as when talking with colleagues and so on. So if you think about traditionally embedded platforms or embedded software systems, the students who were training to those areas, coming from electrical engineering background, microelectronics background, or maybe a bit of computer science background and so on, right? And then when you think about someone who is actually doing machine learning training or doing, federated learning or active machine learning in general, comes more from a computer sciencey mathematics background and so on. And there is a clear mismatch between these two groups, right? Now, it is very difficult to find someone who actually can write embedded code and can also understand, machine learning training regime. You will not find that many people. I mean, we know that. I mean, many of us here are in the industry. We know that it's a very rare regime. So in a way, I think it's an interesting opportunity for academicians as well as for educators to actually think about having a program where these things comes together, and you train your students in these disciplines in parallel, so that they can build up that skill set. Because today, what happens is typically after your degree, maybe you trained in machine learning and then you picked up embedded systems, or the vice versa. You did embedded systems and now are picking up machine learning, right? So it's very difficult to find students coming out of the university that they can do both, right? I mean, so it's an actual opportunity for academics to really think about having a dedicated program in that, which I think would open up. Now, I know, for example, Amanda's work and many other universities these days are having robotics as an active program, which I think will bring some of these topics closer, right? But in generally, I think there is a lack of skills and that's why also what Ilias was saying, that the development has been quite slow with respect to the other areas.
Definitely. In federated learning, let's pose it as federated teaching is an important factor to think upon, at least when it comes to academia. So there are a lot of technical challenges to adopt federated learning, but there is also the siloed version where you have a small number of entities that want to collaborate, but essentially they can't due to privacy issues, due to legislation, these being hospitals, these being insurance companies, and so on and so forth. Do you see this as being like the first step towards proving where federated learning can go, and then use this as a middle step to adapt federated learning to other use cases, or not? And this also comes into Fahim's comment about legislation and data ownership, where in the area of health makes a lot of sense. Whoever wants to comment on this, please go ahead.
If I can jump, I would say this, in my mind, a cross-company or silo federated learning is actually harder than user-based federated learning. And my argument is all of these companies have their legal departments, and these legal departments to decide any kind of information, even if it's after differential privacy, secure aggregation, guarantees, running things in the secure enclave, you name it, they will still, from a legal point of view, consider this a possible way of exposing private information, especially if we are talking about information that is highly regulated, like medical information. So for them, it's a very big step to allow that. However, users are more used to wrongly click on user agreements and being able to share data. So for them, it might actually see a better scenario than what the current status quo, which is sending everything to the cloud. So in my mind, I would say that it's from a legal kind of regulation point of view, it's easier to do this with the users. That's my take.
Yes, I can see that.
One thing I want to say here, I mean, of course, we have a lot of colleagues from Samsung, which is kind of like a forefront on the device business and so on. But me coming from more, Ilias was also Telefonica before, so I shouldn't say that. But me coming from more traditional telco companies, I think there is a massive work needs to be done to basically make our legal team realize these issues, right? Because it's incredibly hard to actually talk to a legal team about. I mean, I can tell you that, like sometimes we try to release our data sets, right? And it's just a nightmare to do that, right? Because it's not just the question about the anonymity, but it's a question of, like a border control, export control, where the user is, and, even your hosting your services in one country, but one of your users is in a different country, what are the rules there, regulations there? And there are a lot of, I would say, fuzzy lines, right? So, for example, in my case, I have good colleagues like Amanda and, like University of Cambridge who are willing to take over some of our responsibilities. So they do that, right? But that's a very rare case, because traditional telco or infrastructure-based companies, I think these issues are extremely, extremely complex and extremely complicated. So the frameworks needs to be developed, but that framework itself, it's going to be a mess. So I think it's not going to be an easy ride.
Great, thanks a lot. Let's move to the next subject, which also has a lot of interest. This is with regards to collaboration and offloading of computation from mobile agents to ambient local devices. So there has been a frenzy streak of developments in hardware in the recent years, ranging from developments in highly specialized hardware, such as NPUs or ASICs, to reconfigurable fabrics, such as FPGAs. However, the same can be argued for the most accurate DNNs as they become more heavyweight and resource hungry in the pursuit of extra capacity for additional accuracy points. At the same time, mobile network bandwidth is expected to rise significantly with the advent of 5G and Wi-Fi 6, for instance, out in the wild. Collaborative computing has been around for a while as a mechanism to speed up execution by offloading computation to faster remote endpoints. As more and more connected devices enter our homes, is it possible to expand from a smart device to a smart network of devices? And let's start with Amanda. And I want to ask you, robotic assistants, let's say, are they? So as you mentioned before, the models deployed there are mainly centralized in the way that they are trained. So the collaboration between agents, can it give extra information or extra signals that can prove to be beneficial accuracy wise to the task given?
I could talk for hours about this subject. So learning collaboration and so learning how to collaborate, learning how to cooperate is actually at the core of my research mission. And it's a really difficult problem. So in the multi-agent, multi-robot domain, we kind of classify the solutions to these problems into algorithmic areas. One solves them through centralized, optimal, non-approximate methods. The other looks at it by trying to develop decentralized, approximate methods, and approximate in the sense that they should converge or asymptotically converge to the same performance as optimal centralized solvers, right? Now, taking a step back historically, designing decentralized policies from scratch by hand through first principles-based approaches is really, really difficult, let alone when you start including, the realness of the physical world, heterogeneity, and all of that. Which brings me to machine learning, which is really, so this idea of learning coordination, learning how to decentralize policies, learning how to interact and collaborate with other intelligent, potentially mobile agents is a really hot topic right now. And a small group of us from the multi-robot, multi-agent domain, or people looking at, inter-vehicle collaboration, are actually studying the problem of what machine learning architectures can we use to learn coordination patterns, to learn coordination policies. And, there are different ways of thinking about this. Myself and a few others in my kind of research community, we've actually been leveraging a machine learning architecture known as graph neural networks. They're actually more popularly known within the domain of node inference, link inference, and social network kind of area. We're using a completely different framework. We're thinking about leveraging graph neural network architectures to learn the signals that you're going to send across the edges. So it's a different way of thinking about it. And one of the reasons that we're using them is because even though the formulation of GNNs, so graph neural networks, is centralized, you can decentralize these modules completely. So the modules are carried locally on the individual agents. And as soon as you work through the math and think about it that way, essentially what a local GNN can do for you is it knows how to aggregate incoming information, and it knows how to process that information, and it tells the agent what it's got to do with that. And that is a super powerful idea, because what this means is that the parameters that the GNNs are learning are the collaboration parameters, because the agents are getting incoming information. They know what to do with that data stream, and they know how to update their, their local state as a function of what they're getting. That is collaboration, right? If you design your incentives correctly, if you design, your reward function or whatever learning paradigm you're using, imitation learning, supervised learning, whatever it may be, right? And so this is really exciting for us, because we're now at this point where we're thinking of learning collaboration, cooperative policies, and it's opening up a whole panacea of new problems or new ideas that we can now start to think about. Can we use machine learning based, GNN based architectures to deal with heterogeneity more efficiently? We can learn heterogeneous communication policies. We can try to get around all of that, and maybe kind of touching base on one of the things that you said before, sharing compute responsibilities. That's something that you can learn as soon as you make your agents in your system heterogeneous, and you tell them, well, the guys over there at the roadside, they have more compute because they're sitting on the road, and maybe the vehicles that are passing by have to deal with information very quickly and have to, how can they collaborate given that the features that they're sending themselves say something about their heterogeneity? And all of this we can do through data-driven approaches. Now, of course, the question is, as with any machine learning-based approaches, how do you know that what's being communicated leads to desirable outcomes in a cooperative or collaborative sense? And this is actually also part of some of the research that we've been doing, and I think a few others as well in this community. So how do you know that the collaboration or the cooperation that emerges is cooperative and not adversarial? How do you know that what's going on, what's being sent to agents is benign and not malicious? And here is where maybe it's less of a panacea, but more of a Pandora's box, because we have to think about these issues as well. And then we're getting into the realm of interpretability or reliability or provability of the policies and all that. And I think, we're just starting to scratch the surface, basically.
Great topics that you touched upon. Is there a critical scale for this for graph neural networks to coincide with the physical deployment of robotic agents?
So do you mean scale as in
like you need
during training
of robotic agents for this to work?
Super cool question. Actually, so generalizability, I think, is the key word here. So we've been looking a little bit at that in the sense, if you train your GNNs with 10 agents, can you deploy it on thousands? And we just have a paper up on arXiv that looks into how to do that. So, I mean, it's a research question. We don't have, this is the, one-fits-all answer. And it certainly doesn't come for free, because the problem is, or the fundamental philosophical question behind all of this is the coordination problem that you're trying to solve fundamentally modularizable, right? If it's modularizable, there's no reason why a pattern matching strategy such as machine learning can't just learn, policy in training with 5 agents and then you deploy it in thousands or even millions, right? But the problem is that many of these coordination problems are not completely modularizable, because they rely on, there's some level of global information that is important to the coordination of these systems. And that little bit of information, that signal, is important to the system. And that's why generalizability, I think, is not, it's not a solution that comes for free, and you need to think about how to get it. And solutions within the machine learning area, within the, using GNNs or whatever paradigm it may be, we need to think about this. Again, so, we can show generalizability to a certain extent, but for each problem that you're considering, for each application that you're considering, I think you have to look at it renewed and think about specific solutions to how to solve the generalizability problem for those given applications that you're trying to solve.
Great. Thanks for the thorough answer. Ilias, coming to you. Do you think that the future of machine learning inference is shifting towards hybrid computation, such as local plus offloading to a nearby or less nearby, further away device, or going fully local soon enough, in the sense that hardware advances are coming every year? And can you also comment on the privacy leakage of offloaded models in your narrative? Thanks.
Yeah. So practically, the advances on hardware acceleration are there, and they will start being evident on mobile devices. But at the same time, as I said in my talk, the models are also becoming almost grow exponentially in complexity, especially if we go in the speech domain. And it's very hard to chase the accuracy that these models are having by running them on device. And there are two reasons there. And one is the thermal dissipation of these devices. They will always have to actually be hundreds of watts. They can only consume hundreds of watts in terms of energy, less than a counterpart running as a desktop. And the second is they are battery operated, so you cannot do much unless you're willing to sacrifice some part of the energy. However, I see as a future direction that these devices will be running more and more of the simple tasks on device, like simple image recognition and so on, and maybe just offload the more complex tasks. In terms of offloading, the big challenge there is if we are talking about 5G edge computing type of offloading, edge computing infrastructure can be quite expensive, because from when you compare this to cloud computing, in cloud computing you have to support the data center that is central, and you have a building, security, cooling, everything, so you can bring the cost down. But if we go now to edge computing, you have to maintain thousands of different sites across a country, distributed. It's a much more expensive scenario. And who owns them? Is it the MNO, the ISP? Is it the service provider, is it like a CDN of computation this time instead of throughput? So I don't think this model is mature enough, especially due to the fact that there's no more common API or let's say standardized way of selling this kind of resources to application developers and building kind of the common infrastructure. But it's something that people have been writing quite a lot about in academic papers as the future in offloading computation. What I see as a more realistic scenario of offloading is the in-house or in-office or industrial kind of offloading, where you offload computation. For instance, you have your ecosystem in the house, and it could be an Apple ecosystem, a Samsung ecosystem, or whatever, and there's a hub that essentially has a GPU and maybe can support the robotic assistant that runs on battery power, and then you can actually lower both the thermal and the battery requirements of this robotic assistant and still run your 5 or 6 models that you need to run to navigate an environment, to understand the users in terms of speech and gesture and all of these things that you won't do in a robotic assistant. So I think this is the thing that will catch up. And in an industrial environment as well, you have all this kind of, like in a warehouse, all these robotic things like hands moving things around. Maybe there you can have some edge computing, offloading computation from much simpler devices and sensors that you embed in the environment for safety or coordination. So I think it will start there, and then once the 5G edge computing kind of environment is more mature and all the legal and ownership issues are resolved, then it might actually go in this direction as well.
Yeah, thanks for the answer. You actually sent out breadcrumbs in order to ask further questions to each of the participants. So okay. In the sense of the communication standardization, this needs to be standardized for interoperability in order to attain a critical mass, in order to become the norm. Is that correct?
Exactly. Like imagine, I'll put my ex-Telefonica hat. Imagine if Telefonica deploys an edge computing capability and says, hey, we're selling this resource now. These users will connect to Wi-Fi. What are we going to do with their computation then? These users might roam around or might actually start connecting to other networks. What's going to happen with their computation then? And if you're, let's say, an application developer, when you deploy your application, you require offloading. can you support only customers that are in one specific MNO that is selling this offloading capability to their edge computing? No, you actually have to sell a service that works across different mobile network operators, more and in a transparent way, more or less how the cloud works today, where it doesn't really matter where you're connected or how you're connected, it just works. So we're very far away from being able to do that.
Mm-hmm. And then you touched upon the topic of having a hub that is sharing compute in this sense. But previously, Dimitris mentioned a hub sharing data, essentially shuffling data between amongst one another. I want to ask Dimitris in that, with that regards, how important does he think the encoding of the information for upstream and downstream communication when collaborating is? Do lossy mechanisms, for example, work up to a point based on the distributed representation in neural networks?
Yeah, that's a very good point. So, so my group has been working a lot in trying to encode communication more in the sense of compression and kind of like quantization. I think there's been a ton of work in that area, right? So especially, I think in the context of federated learning, this is extremely valuable to think about because for some models, communication could be the bottleneck if the models are large enough. So we've definitely, there's a lot of techniques that people use, and there's a lot of techniques that people have come up with, and we kind of like know and understand how the trade-offs are driving algorithmic design and how far we can go. And it does seem that, with high capacity models also has high compressibility, right? So there's all this interesting work about, both compressing gradients like, QSGD and Atomo and Turing-Grad, but also how you can quantize and compress models similar to, deep compression or, the lottery ticket hypothesis. So I think, there is definitely a big opportunity there for encoding mechanisms to preserve, or I should say to kind of like save up on communication. But then at the same time, the problem is that if I make my model smaller, or my gradient smaller, that doesn't necessarily mean that my communication would be, smaller, because I have to actually change my communication protocols to whatever support sparse arrays and whatnot, right? So I think that's an interesting question that we kind of we always come back to, right? We're like, okay, in theory, you can compress stuff and you can make this fancy data structure, but well, can you change your framework to support this data structure? Is it is it worth doing that, right? So, I guess that's maybe the major, I would say, challenge with regards to adoption for these types of, quantization or compression type of encodings.
This begs the question, though, that are we heading towards some research on co-design of these components, or are they completely siloed and one leads and the other follows?
Yeah, I think that's a great question. So if you were to co-design, things would be much better, right? So if you were to co-design data structures and whatever compression techniques, then you'd say, okay, we'll kind of figure out what's the best way to encode and represent, a compressed model or a compressed gradient. However, usually this co-design sometimes restricts the design space of future, encodings, right? So maybe, I don't know, 5 years from now, some amazing group comes up with a different encoding technique that requires a very different data structure. But that technique may not be supported by the current sort of framework, right? So I guess what do you do then? So I think there is this trade-off of kind of leaving the design space flexible enough for other people to adopt their sort of solutions, but then also striving for doing a little bit of co-design. So I'm not, I haven't really done any co-design for sort of, frameworks like, TensorFlow and whatnot, but, I guess I'm just coming back to that point that it's definitely always a question of what is supported and to what extent what we do in theory can be translated in practice, and it's still to me a bit unclear as to what we can do. And I guess one point I want to say is that the most interesting thing, I've been working in model compression and gradient compression for maybe the past 3-4 years, and in all of the theory papers or optimization papers at NeurIPS and ICML, you see all these guarantees about, we can make something 1,000 times sparser. But then, if you actually try to implement that, you actually do not see any benefits, because it may be expensive to do the encoding and may be just hard. How do you transmit 5 numbers that are sparse, right? You have to transmit a sparse set of indices, right? And then this can actually lead to communication that's actually pretty similar to what you would do in the unspecified case. Anyway, so that is to say that I think there's very interesting questions in the kind of interplay between data structures and what you say, the co-design between them, communication policies, and then the actual gradient compression mechanisms.
Great answer. I really enjoyed that. And the last one, Ilias, you touched upon the topic of the industrial deployment and offloading to nearby devices. And I guess that Fahim is the most appropriate person here, at least based on his talk, to talk about this issue. Fahim, would you like to comment on where do you see offloading happening in industrial setting? And let's say, does it make sense, compute or energy-wise, to do so?
No, I think with NVIDIA's innovation in the industry of edge hardware, I mean, we have seen these recent AGX boards and Jetson boards. I think they are remarkably powerful. So my hunch is, or not hunch, I'm pretty sure that's going to happen, is that we're going to see offloading, but this offloading would still be limited to your campus. So, I mean, there are a number of projects, in fact, in our organization too, where we are building private network-based solutions. So where basically the whole idea is that a network in a box, you go and you deploy your entire network infrastructure within that campus. You have your own LTE or whatever 5G or cellular connectivity you want. And we also started seeing that these solutions are coming with their edge infrastructures, that all the machine learning based services are happening very locally, not necessarily on the device itself. They're doing 1 or 2 hops, but those hops are limited within that private peripheral. So I think it's a common trend that's happening today, and I only think this will increase and will sort of like expand across verticals. So yeah, I mean, offloading would definitely be a key proponent in pushing these techniques. In, you know, I mean, as you all know already, that the carrier application is their video analytics, right? The live video analytics for safety and surveillance applications. I think once a few more industries start putting their hat on that solutions, this will only become increasingly mainstream.
Great, thanks, Fahim, about the comment. And coming to an end, to close the circle, Amanda started with heterogeneity in robots, and dealing with that is indeed a very big challenge. Do you see? So let me say it in a different way. If collaboration is enabled between agents, or between agents, or between agent and, let's say, a charging station. So that would be, for example, a robotic vacuum cleaner could have a GPU in their base station. That's a completely irrelevant suggestion, but just illustrating an example here. Do you see this as being a way to make the environment more homogeneous to tackle this challenge? And if I may put it in a different way, let's say a mobile phone is something that you change once per year, once per 2 years. A robotic agent is something that you change every 5 to 10 years. Who knows? Is there a way to future-proof such an investment with modularity over different agents or like different components?
Yeah, great question. I like the attitude. Very constructive. I think heterogeneity is just a really difficult topic. I think also falling back on a lot of the things that Fahim says. As somebody who has a lot of deep experience in embedded systems, the issue with collaboration and cooperation in systems where you have heterogeneity is not one of, okay, let's try to see if we can model them as homogeneous systems, but it's one of, what are these pairwise relationships? What features do these pairwise relationships really depend on? And if these features are so deep down that it's like, hey, what is the status of my battery, for example, and mine is slightly different than yours, even though we're the same device potentially, then our machine learning systems have to learn that that is a feature that matters. And if we're now looking at devices across scales where the heterogeneity is just, it's stratospheric, the possibilities of heterogeneity are stratospheric, I literally have no idea how to tackle this problem at this point, right? Because we're really talking about, we want to kill all the birds with the same stone. And I don't think that right now we're ready to do this with the machine learning tools that we've developed thus far, or the training paradigms, to put it maybe a little bit more precisely, because there's just so much richness in the problem. But I don't know, maybe there's a way of taking the problem apart and thinking about it slightly differently, more constructively, and maybe sandboxing the problem a little bit better so that we can perhaps tackle it and try to model them as slightly homogeneous systems in some way or another. But I don't really have an answer to that.
Yes. All right. Thanks a lot for the reply. So before we move to a short Q&A, I would like each one of you to pose one challenge or one, let's say, innovation that they're excited about in the shorter or in the longer run that is coming about in each one to their field, and then we can move to Q&A from the audience if there is anybody left actually in this time. Whoever wants to start, by all means. Ilias, would you like to start?
For me, the biggest challenge, I think you asked about challenge.
Challenge or innovation that you're excited about.
Yeah. For me, the biggest challenge, going back to the federated learning landscape, the biggest challenge is, one, the ability for us who work in this area and for the whole academic world, so both industry and academia, the availability of realistic data sources that have non-ID distributions. So large-scale data sets that can help people prove things about how quickly their algorithms converge, how much they can be compressed, how much they can be personalized, whether meta-learning can actually be used to do faster personalization. All these things that require some distribution that is actually there in the real world, but we only emulate here in the lab, is something that I think it's critical, and the research community should actually find a way to solve. So that's the thing I would try to solve first before anything else.
Great, thanks a lot. Dimitri?
Yeah, so I agree. Kind of like the biggest challenge is, and I guess this comes back, like every time I do like some research in federated learning, we run experiments or whatever, FMNIST and whatever, C410 and ImageNet, and then what does it even mean, right? I mean, I can convince myself and my colleagues that the theory and optimization, but I mean, does that even mean anything interesting? And we've been asking people from the industry to share stuff with us, and they're like, yeah, we will share stuff with you, and they never really share data, right? So I think big companies like Google and whatever, Apple, they just already have a ton of researchers and engineers that are working on this. And I'm sure they're happy that we're excited about federated learning, but I don't know to what extent they can or want to share data with us. And I think that's a big challenge, right? So I can convince myself that I do serious stuff in federated learning, but at the end of the day, that the kind of like the performance that I'm seeing and I'm testing in whatever experiments I have is just a proxy for something I have no idea is going on in practice. So that's the biggest challenge. And for me, to be honest, the biggest point of, let's say, disappointment maybe of the area, that, it's kind of like, it's just very hard to test stuff, right? I think in terms of excitement, I'm glad I wasn't first, because the more I do research, the more jaded I get, and the less excited I am about things. But I think the part that I'm most excited about is the area of network pruning. So I used to be, extremely uninterested in network pruning up until the lottery ticket hypothesis, and then I became extremely interested in network pruning. And there was this really cool paper that basically said, not only, there's this idea of lottery tickets and you can train magic subnetworks at initialization and all that. So there was kind of like a bunch of follow-up papers that basically said, you don't even need to train anymore. You just need to prune, okay? Give me a binary network, ±1, with whatever activations you want. I can kill off edges and I can make it as accurate as you like. And yeah, you're gonna have a sparse network that everybody has to use, and then I kind of like kick out from the window, real numbers, accuracies, floating points, everything, right? So this actually, and we've been discussing with some hardware folks from Yale about the implications of this idea of like just pruning binary networks and how in terms of hardware this can be beneficial. And I think for me I need more time to explain more details about this, but it does seem to me that like this, for the first time, there's this kind of like small window of opportunity where we can do things without using backpropagation, where just like combinatorial pruning algorithms, which I think is spectacularly interesting and has a lot of implications in on-device training and of course inference. And I've been spending a lot of time recently kind of like focusing on that, and I think that's the thing that I'm most excited about these days.
Great, thanks a lot. Fahim?
Maybe one 3,000 feet challenge, which is I was suggesting before, is moving from system 1 to system 2 level reasoning engines. So I think if we want to make machine learning really useful for a human, we really have to push the boundaries a little bit. Although we talk a lot about nitty-gritty details in optimization and architecture and so on, but I still find that a machine server is stupid. So we should really try to push the envelope a little bit. But that's a really very 3,000 feet high challenge. And maybe more 30 feet high challenge is what Ilias said. I think we need to create a very well designed, grounded on sound principle, a data synthesis engine, right? So I will provide that this is my hardware, this is the environment, this is the sensor, or this is the signal I'm looking for, and my engine should give me a realistic data. Right now, however you generate that data, whether we use generative modeling technique or some other form of, network architecture, I don't really care. But I think we need a very principled way of synthesizing data if this data-driven approach has to go long way. Because otherwise, I really feel that for real-world sensing systems or real-world data-driven systems, we will have significant problem building mission-critical applications using these kind of approaches. Simply because of the lack of data we have.
Thank you. And Amanda, what's your
Sure. I'm going to keep it really short. So my first one is, well, the big challenge, and it's actually really related to what both Fahim and Ilias said. Just in robotics, we call it sim to real, because we don't generate data, we need interaction because it's about control. So we talk about simulators. So I think sim to real is one of the biggest challenges right now, because people get things to work in simulation and then you transfer it to the reality and nothing works. So that is, I think, one of the biggest areas more people have to think about more carefully. And what am I excited about? I think personally, this idea that we can learn communication policies to enable cooperation and collaboration. So really from a data-driven approach, I think that's super exciting. And I think, GNNs, that's just one way, one framework of thinking about it. There might be others out there, and we're just beginning to look into that. And I think that's really, really cool. So that's all from me.
Great. Thank you. Thank you, everybody. So if anybody has a question for the speakers, shortly we can allow for 1 or 2 questions because we have already been overboard. Please type in or just raise your hand in Zoom, and I can give you the floor. Crickets here. Maybe I'll check Slack as well. but there doesn't seem to be any. Well, even without questions, I really enjoyed my time with you guys. Hope you did too. And thanks a lot for participating. I hope the next interaction that you will have will be probably in a real life environment, not virtually over a Zoom call. Thanks a lot.
Soon, yeah. Thank you very much. It was great.
Thanks a lot.
Thank you so much. Have a great day.
You too. Cheers.
Thank you, guys. Thanks a lot. Thank you very much.
Yes.